Okay, time is 11 o'clock, so let's begin. Project number 1 is due now. If for some reason you were unable to email it to me, please come talk to me after class. Also note that whenever I receive your project, I will always reply to your email saying thank you, I got it. So if you didn't receive a thank you message from me, that means I did not get it. You should come talk to me after class if that happened to you. So today we will finish up Chapter 2 and then start Chapter 3. Are there any questions? Okay. We left off on page 240 in the notes. So we were simply talking about this type of hypothesis test involving our regression model. Beta 1 is equal to 0, beta 1 does not equal 0. We had already looked at previously one way to do this test, often referred to as a T-test, because a T-test statistic is used. At the end of class last time we looked at another way to do it, which is often referred to as an F-test, because an F-test statistic, an F distribution is used to actually perform the test. I will talk about shortly about why are we talking about two different ways to do the same thing. But for now, let's take a look at how we would actually implement one of these F-tests in R and actually then perform the actual hypothesis test. So this is with the high school and college GPA data once again. I'm going to use an alpha level of 0.01 for the test. And let's say I have my data in GPA like usual. I estimate my model using the LM function like usual, and I summarize the fit of the model as well. The key portion of this output is highlighted. Notice it says F statistic. This is what we defined previously as F star. Also notice you have a p-value there as well. We're going to use that for our hypothesis test 2. We'll come back to this ANOVA function in a little bit. So step 1 of a hypothesis test, and again I expect to see all 5 steps always listed out when you do a hypothesis test like a test or a project. This way it helps me grade, and also what I will do is assign points to each part of the 5 parts. So step 1, I'm going to state my hypotheses. Beta 1 is equal to 0 versus beta 1 does not equal 0. In the context of this problem, remember what beta 1 equals 0 means. Basically means that high school GPA is not linearly related to college GPA. Then my statistic, F star, we found the output to be 91.38. Step 3, state a critical value. Last time we talked about this is the 1 minus alpha quantile from an F distribution. And in this case, I'm looking for the 0.99 quantile. Degrees of freedom for the numerator is 1. Degrees of freedom for the denominator is n minus 2, or 18 in this case. And you get 8.29. You can find that easily in R using the QF function, quantile F distribution. So to draw out what we have going on here, here's what the F distribution looks like. It looks something like this. It's not drawn to scale. And basically, what we just found is this critical value for the hypothesis test. If I have an F star or a test statistic value that falls to the left of it, I don't reject HO. If it falls to the right, I reject HO. If it falls to the right, basically what this means is that this F star value is unusual to have if the null hypothesis was really true. This again just goes back to the basic ideas of what hypothesis testing means you learned about in your very first stat course. In our case here, 91.38 is obviously larger than 8.29, so I reject HO. This means that we have scientific evidence that high school GPA is linearly related to college GPA. Well, what about a p-value? Well, remember what a p-value does. Instead of comparing values on that x-axis of that little distribution plot that I drew, now we're comparing areas underneath the curve. So in this particular case, let's say that I have a random variable A that has an F distribution. Then the probability that A is greater than 91.38, as you expect based upon how I drew that distribution, is very, very small. So if the p-value is small, of course, you reject HO. Okay, so that's our hypothesis test. Now, this F test that we just talked about is actually equivalent to a T-test that we talked about at the beginning of Chapter 2. If you remember, at the beginning of Chapter 2, we focused on this value right here. This was our T star, and this was the corresponding p-value, 2 times the probability that a random variable, let's say A, where A has a T distribution, the corresponding degrees of freedom, is greater than the absolute value of 9.56. It's 1.78 times 10 to the negative 8th power. Notice how that p-value is exactly the same as what we got with the F distribution. And in fact, this 91.38 ends up being the square of T star. Now, if you took a course like Stat 883 here, or Mathematical Statistics 2 class, you would actually prove that indeed that a T distribution is the same as an F distribution. For us, of course, we're not going to prove that, but this is why this is all occurring here, is that a T distribution is equivalent to an F distribution when that F distribution has 1 numerator degrees of freedom. So I outlined this then on page 242. So we have 2 ways to test the same hypotheses. Beta 1 is equal to 0 versus beta 1 does not equal to 0. Starting in Chapter 6, though, we will learn about models that look like this. Expected value of y is equal to beta 0 plus beta 1 times x1. Let's say you have one predictor variable, plus then beta 2 times x2, a second predictor variable, plus, and we could go all the way out to, let's say, just to be general, the pth predictor variable. And we might be interested in doing hypothesis tests about the one or more betas for that particular model for obvious reasons, same as before. You know, if a beta is equal to 0, that says that particular variable does not have an effect on the expected value of y. Well, in order to test this, where HO is beta 1 is equal to all the way up to beta p is equal to 0, we can use a slightly modified version of this F test. A T test, though, cannot do that hypothesis test. Instead, what you will learn about in Chapter 6 or 7, that a T test can only test one beta at a time. So why are we learning 2 ways right now to do the exact same thing? It's because later on, they will not necessarily be able to do exactly the same thing. That's why. Let's also go back here. Now, if you remember from last time, we talked about an ANOVA table, analysis of variance table. And let me do a split screen with what we had presented last time. There we go. There it is. And if you remember, we looked at how one could partition the total sums of squares that one could have if, let's say, you use y bar to predict y. And that was represented by what we called SSTO, simply the sum from I equal 1 to n of y sub I minus y bar squared. So it's like your total possible variability that you could have. And then what we did was we actually partitioned it into 2 different components resulting from regression. So the sums of squares due to regression, meaning the part of SSTO that now I can account for from doing my regression model, If I were to add that then to SSE, sum of squared errors, the sums of squares that are left over from doing the regressions, meaning my squared errors, SSR plus SSE is equal to SSTO. And this is called an ANOVA table. All of you should have seen an ANOVA table before you came into this class. It's a topic that's taught in 801. But this is what it looks like in a regression context. And if we use the function ANOVA with the result from the LM function, which I call mod.fit, you get that exact ANOVA table. So notice, well, it's written a little bit differently. Notice you do not have this total row. Why? Well, of course, if you just add down, you get the total row in that table. Okay. Are there any questions? Okay, let's move on then to section 2.9. So we're going to continue looking at these sums of squares, but we're going to look at it in a little bit different way. Now also, if you remember from last time, we had this plot in the top portion of the screen here. And what this represented was the high school and college GPA data set where I've highlighted one particular point in the plot. And the pink line represents then the sample regression model. The orange line represents a horizontal line for y bar, representing if I didn't have any knowledge of x at all, well, how would I predict y? Well, just a sample. And so then if we looked at then the error in trying to predict this particular point, we would take the distance of yi minus y bar. Now, if we now acknowledge the fact that I have this x variable available to me, this predictor variable, and we do our regression analysis, put the line on the plot, we can see how our prediction error decreases. And so what information now have we accounted for then by doing this regression analysis? That's what's represented by this distance here. So if I square all these quantities and add them up, I'm going to get SSTO. If I square all these quantities and add them up, I'm going to get SSE. If I square these quantities and add them up, I get SSR. So you might be thinking, well, let me put it this way. You know, obviously, the closer the point is to that regression model, that line for the regression model, the pink line, you can say the better our regression model is doing in predicting, right? So what you might be thinking is, well, since SSR plus SSE is equal to SSTO, maybe I could take a look at a ratio. You know, maybe look at SSR divided by SSTO, and that gives me some information about how good my model is. And in fact, if SSR was very close to SSTO, what do you think that would say about your model? It's going to be very good because that means SSE is very, very small. So thus you have very small residuals in absolute value. And thus your model is doing a very good job of predicting your sample data. And so because of that then, we have a measure which we simply call the coefficient determination. Most people symbolically denote it by R squared. I'm not for sure why it's called R squared, but that's the symbol that's typically used for it. And so if we take SSR divided by SSTO, that's our R squared. Of course, this also means I could take SSTO minus SSE, that quantity divided by SSTO. And what this represents then is it's a proportion. So you can think of it as, let's say, the amount of reduction in the total variability by doing the regression analysis. Another way to think about it is the measurement of how much we have improved in estimating y by using x instead of just using y bar alone. We want this to be as large as possible if you want your model to work. So R squared is a proportion. It's between 0 and 1. Another way that you can put you can say what it's measuring, 100 times R squared percent of the variation in Y can be explained by using X to predict Y. Just another typical interpretation. Perhaps this little diagram here is a little bit misleading. So the purpose of it is saying the closer you are to 1, the better the model fits the data. The closer you are to 0, the worse the model fits the data. However, if you have an R squared of 0.1, that does not necessarily mean that you should throw away your model. Because in some applications, knowing 10% of the variability in Y is explained by X is a good thing to have, good thing to know. Otherwise, you're at 0. So just because you are close to 0 does not necessarily mean that the model's bad. It just depends upon your application of interest. You know, is 10% meaningful or not? All of you should have heard of a coefficient of correlation before. Well, simply in this setting, when we have one predictor variable only, if I take the square root of R squared, I get the coefficient of correlation, where I put a positive or negative there depending upon if I have an upward trend for a positive relationship or a downward trend for a negative relationship. Okay, let's take a look at a quick little example of doing the calculation. So this is using advertising to predict sales again. We've already calculated SSTO and SSE before, and so for R squared we get 0.817. And again, what this means is that 81.67% of the variation in sales can be explained by using advertising. You'll notice that it says also that there's some stuff that's not explained by advertising. Let's take a look at a scatter plot of the data, and you can see why we had such a large value of R squared. You know, we see these points are relatively close to the line. For the high school and college GPA example, here's just the output that we've seen before. The key portion of the output that we look at here is what's highlighted. R calls us multiple R squared. That's just simply our R squared, our coefficient of determination, 0.8354. So again, what this means is 83.5% of the variation in college GPA can be explained by using high school GPA to predict it. Note that you see something next to it called an adjusted R squared. This is something that we're going to talk about in Chapter 8, I believe. Yeah, Chapter 8. And it actually might be Chapter 9, just later in the course. And this is just an adjusted version of what we just saw for the formula for R squared. We'll talk about it at a later date. Well, remember that college GPA and pizza example, you know, the number of times you eat pizza? Let me go back to the output for that. So this was the output that we had earlier in Chapter 2. And here is the R squared, 0.001. So 1% or 0.1% of the variation in college GPA is explained by the number of times you eat pizza. Very, very low, suggesting that eating pizza is not necessarily a good predictor itself of college GPA. And that makes sense from looking at this scatter plot with the estimated model on it. And in fact, if I wanted to, I could plot then a line for Y bar, and it will look something like that. Notice how the regression model represented in red doesn't really change much as a function of X. It's very similar to the line for Y bar. That's why our R squared was so small. Okay, any questions? Talk about some warnings about using R squared. So it's a measure of fit of the model. How well does our model fit the data? Does it fit good? Does it fit maybe poorly? But you have to be careful when using it. If your sample size is quite small, your R squared might be, let's say, artificially inflated. An extreme example of this, I'm sorry, if your sample size is small, relative to the number of predictor variables you have in your model. An extreme example is that let's say that I have one predictor variable and I have a sample size of 2. Well, if you were to actually estimate the model, you would get something like this. Notice how the regression model goes through the 2 points. Exactly. Try a simple case on your own. Just verify this to yourself if needed, that this would actually happen. So, what are my residuals? 0. So what's my R squared? 1. So you might be thinking, oh, wow, I have just come up with this great scientific discovery that this model perfectly predicts my Y. Well, you have a very small sample size. And, this R squared is, you could say, again, artificially inflated because it's such a small sample size relative to the number of predictor variables. Right now, R squared is just measuring the linear relationship for the type of model. So if you had, let's say, a quadratic relationship, which we will discuss maybe even a little bit later today, this R squared is not quite capturing it, depending upon the model that you actually look at. Okay, so
I have a question.
Yeah.
Yes, if you have like an R square, like a really little, and
An R squared of what?
R square, a small R square, the small one.
Okay, small R squared.
Yeah, that means like your model is not good.
For
Doesn't mean
prediction.
Doesn't mean like you did a bad job.
Not necessarily. I mean, it depends upon the application itself. Suppose you're doing some kind of exploratory study, and you're just looking for particular factors, predictor variables, that might affect the response. And, going into it, you didn't know what to expect, and let's say that you end up having an R squared of 10% for one of these predictor variables. Well, great. You found an R squared of 10%. You have found that something's explaining 10% of the variation of Y. Would I use this model for predicting Y? Depending on the application, probably not. But you still found something. Here's an interesting story about R squared. I will not use names here, other than the name Oprah. Okay. A student actually who actually graduated from UNL, did an interesting study where the student was looking at, well, what facial characteristics makes people think that you are attractive. And so the student had a number of measurements of the face, like the distance of the nose from the eyes, stuff like that. Okay, so the student had all these measurements. And so basically, these were like the X's, or these were like an X. So, the distance between the eyes would be 1X, distance between, let's say, the nose and the eye would be another X, and so on. And she, yes, it was a she. So, there, I'll narrow it down. She also had people, just random people, look at a computer screen of people of pictures of people, like Brad Pitt was one of them, and people would rate on a scale from, I think it was 0 to 10, their attractiveness. So people might give Brad Pitt a very high score, let's say. So using those ratings and also the measurements of like Brad Pitt's facial characteristics, they fit a regression model. Got an R squared about 0.25, if I remember right. It was something that wasn't, let's say, 0.9, but 0.25, maybe 0.3 at most. Okay? Got the work published. Well, of course, people find that kind of stuff interesting, and so started making national news, international news. In fact, I don't remember which paper, but I remember seeing something, one of the big papers in London carried this research, talked about this research. Well, Oprah found out about it, and actually invited this graduate of UNL to go appear on Oprah. And one of the things that they had on the show was they were showing these pictures that came up, and they had I think they had the audience maybe even rate, the attractiveness, and maybe even compare it to the model. what the model would say. And so, you know, Oprah would show a picture of Brad Pitt, and, oh yeah, we think that he's attractive, and then show a picture of someone else. Oh no, that person's not attractive. And Oprah, you know, was just like, wow, this is cool, you know, that we can use science to do this. But again, should we get all excited about an R-squared of 0.25 when we're talking about prediction? I don't know. I think not. I think not. But it helped this person's career. So. Anyway. If you remember, towards the beginning of the semester when I first presented this model, I said that x was, you need to think of it as a constant. It's a fixed value. Well, in actual applications, x is usually random. For example, with the college and high school GPA data set, I would expect x to be a random variable. Because, you know, you don't know what these high school GPAs are before you start sampling students. So what happens then if x is a random variable versus a fixed quantity? And as I've briefly mentioned before, basically all this stuff that we've been talking about holds true. But there's one small thing that you have to, that you would normally do if you want to be totally specific, is that in your model statement itself, instead of just saying the expected value of y, say expected value of y given x. Now, depending upon your background before you came into this class, you may have not heard of conditional expectations before. All of you should have heard of conditional probabilities, like probability A given B. Well, if you haven't heard about conditional expectation, just kind of think of this, interpret this like you would a conditional probability, meaning that given x occurs, now what's the expected value of y? When you make that very small change, then we can state our model like this. All the stuff that we've been doing holds true. If you want a more in-depth description of that, Stat 970 will talk about that. You know, that typically is saved for a higher level stat course because you need to know stuff such as, well, conditional expectations. You need to know about multivariate normal distributions and stuff like that. So, if you want to know more about it, take Stat 970. It's all for next semester. I'm sure now that I told you about that, the enrollment's going to skyrocket. Okay, are there any questions? Okay, let's move on to Chapter 3. Okay, so diagnostics and remedial measures. What this just basically means is this, that first of all, we have a number of assumptions about our model. Let me just write out the model just as a reminder. Let's do a red pen. Okay, so there's a number of assumptions. So these error terms, these epsilons, that's where a lot of the assumptions are. Distributed independent normal 0 sigma squared. How can you actually determine if this assumption is satisfied, or at least reasonably satisfied? That's what we're going to examine in this particular chapter. Another assumption is that notice the form of the model. Basically, we have a linear form of beta 0 plus beta 1 times x. Why shouldn't it be maybe instead beta 0 plus beta 1 times the square root of x? You know, why not? How can we determine if indeed beta 0 plus beta 1 times x is reasonable? That's what we're going to talk about here today. Also, how can you determine if maybe we got some, let's see, non-statistical term, we have some weird things going on with our data, such as maybe in a high school college GPA data set. Let's say that we have some high school GPAs that were negative 0.1. Well, can't have a negative GPA. Obviously, if you don't pay attention to your data and estimate your model with that data error, well, your model is going to be wrong. So how can we make that determination? You know, maybe let's say if you had thousands of observations, you can't necessarily just look at every single one to look for that data error. How can we make those determinations? So that's what this chapter 3 talks about. We're going to do diagnostics on our model to make sure everything's okay, and then we'll talk about what can we do to fix problems that occur, remedial measures. So first of all, diagnostics for a predictive variable. This is relatively simple. You know, what you want to do is look at the range of your x values, obviously. And we talked about this way back in chapter 1. You don't want to do prediction, let's say, outside the range of the information, outside of your observed information. Meaning if you have high school GPAs between 0.83 and 4.32, you don't want to go outside that high school GPA range when you predict what y would be. Also, you want to look for outlying values that may have a strong influence on the sample regression model. What that basically means is that if you have some like really weird x's, that could really have a strong effect on what your sample model ends up being. What I mean by that is that your B1 could change a lot depending upon what x is. This is more of a topic for chapter 10, but at this point the book at least wants to tell you, hey, bad stuff can occur if you have outlying values. Also, outlying values are often a sign that you have a data entry error, as I had discussed a few minutes ago. And so this is just involving the x's, or your predictive variable x. But since we're doing this kind of diagnostics, we could also look at y's too, just to make sure, let's say, that we have no data entry errors. So we'll do that as well. Well, how do we, do 1, 2, and 3 here? Well, we look at a number of plots. We look at just simple summary statistics. It's actually not too difficult. So let me go over here. Let me make this a little bit bigger too. Let me go over here to 10. And so there's my data. I'm going to estimate the model. Let me load this up as well. And the very first simple thing is use the summary function, as we've done before, just to make sure you know what the range of the x's are. So simply put, if I saw that I had a college GPA above 4.0, at least at this university, where you can only go up to 4.0, I'd be a little worried. I wouldn't be a little worried. I'd be very worried, I should say. And I would want to go back and make sure that I recorded the data correctly, or if I can't figure out what's going on with it, I might end up actually throwing out that observation from the analysis. So, everything seems to look okay with our data here. Next one I'm going to do is some graphical summaries. First of all, I'm going to do a box plot. All of you have seen box plots before, but this is how you can do it in R. First of all, what I'm going to do is put a box plot on one side of my plot, and also what's called a dot plot on the other side of my plot, as you can see on page 3.3. And the way that I can do that is basically split my graphics screen into two parts. The function that allows you to do this, or one way to do this, is to use the par function. Par stands for graphics parameters. And MF row stands for make frame by row. So let's say make a frame, a grid, where I want, now I'm combining 1 and 2 together, I want 1 row, 2 columns worth of plots. Then in the first column, I'm going to put a box plot. So I use the box plot function. My x-axis, I'm sorry, we've got to be a little bit careful here. I shouldn't say x-axis. Box plot, if we're just doing one box plot itself, basically you only have, you can say, one numerical axis. And so I say x equal a GPA $HS.GPA. So pull up the high school GPAs. Then I have some options here. what do I want the color inside the box? Let's say light blue. Put a title on the plot, y-axis label, and I have no x-axis label. So let me just go do that real quick. And so there's my plot. Let me jump over here back to Word again. Okay, so that's a simple box plot for high school GPA.
Can you show the average?
Excuse me?
Can you show the average on the Boxplot?
The what on the box?
The average.
The average? Through using just the box plot function itself, I don't think you can. But you could draw it on there if you really wanted to. Basically, there's a function called points, where you could find the mean and use the points function, specify an x value, specify the y value as the mean. There you go. Just as a review, what is represented by a box plot? The middle line is what? Median. What's this top line? Often people say Q3, or you could say the 75th percentile, or the third quartile. Down here we have Q1, which is the 25th percentile, or the first quartile. What's the name given to these out here? What's that? I'm sorry, what?
Minimum and maximum.
Not necessarily. What's a name? What's that? No.
Whiskers.
Whiskers, thank you. You know, some people will call these box and whiskers plots. These are whiskers. Depending upon the software packages doing these whiskers, corresponds to how they are actually drawn. In this particular case for R, I guess always for R, this is how they are drawn. This is the minimum of one of two quantities. Q3 plus 1.5 times Q3 plus 1.5 times the quantity Q3 minus Q1. That's one of the two quantities. And then the other one is the maximum of the x's, without getting too mathematical in how I represent it. So, in other words, you look at your maximum value of x. In this case, it was 4.32. If that is smaller than taking Q3 plus 1.5 times Q3 minus Q1, draw your line here. And in fact, it is in this particular case. So this is 4.32, the maximum in the data set. Otherwise, if that Q3 plus 1.5 times Q3 minus Q1 was less than the maximum of the x's, what would happen then to draw any points that are above that line? What would occur on the plot? What's that?
They would appear as points.
I'm sorry.
They would appear as points. X's.
Label what the points?
They would appear as points or x's or whatever.
Well,
In R.
you would have points that are up there. You would have what are called outliers, as you were saying. So if we had anything above this line here, or this right there, you know, you would have like little points that would be representing outliers. Okay? The bottom line here is drawn in a very similar manner. It's a minimum of Q3 minus 1.5 times Q3 minus Q1, and the minimum of the x's.
The min or the max of those two?
Excuse me?
It's not the max of those two.
Yeah, max. Now, some software packages will always draw those whiskers out to the minimum and the maximum of the x's, no matter what. So you never have any points that are represented as outliers. Other software packages will only draw those whiskers out to, you know, these Q quantities. and that's it, no matter what. R actually does a combination of the two. Okay. The next plot on the right is what's called a dot plot. And a dot plot, all that is just a representation of your actual data represented by dots. So for example, here is the 4.32 that was observed, and here is 0.83 that was observed. Notice I purposely drew these on exactly the same y-axis for both the box and the dot plot. Also, you see the points that are moved a little bit in the horizontal direction. That corresponds to the x-axis direction. That corresponds to what's called in statistics jittering. Points are jittered to avoid overlap. And all it is just a little random quantities added in terms of the x-axis directions to help avoid that overlapping. To do then the dot plot in R, you actually use a function called strip chart, which is what's called. What you want to do the dot plot of, method equal jitter, so you prevent the overlapping. Vertical equals true, so that the points are going up and down. Points, plotting character, just the dot. Title, y-axis label, and there you go. Now, since these points are jittered by a random quantity, I'm going to set a C. Remember how we talked about random number generation when we were talking about project number 1? And that if we set a C number, that allows us to get exactly the same random numbers. Well, if I set a C number here, that always allows the jittering to occur in the same way whenever I produce the same plot. Otherwise, if I didn't do that, I'll show you real quick. Do it twice. Notice I did not set the C number at all, and you can see the jittering is not exactly the same. Okay, so so I did that for X. I did this for Y as well. Everything seems to look okay, so I can move on. So nothing really big there. Let's move on to page 3.5. So yes.
In this case, I can make a decision to not use beta 0 or no.
What about beta 0?
For example, I look at my data, and I find that there is no 0 value for prediction. Can I take a decision don't use beta 0?
We typically always keep beta 0 in the model. There's going to be a case in chapter 4 where we can take it out. But we're going to typically always leave beta 0 in the model, because otherwise you always force then the line, the regression model line, to always go through the origin on your plot. And that could then distort the relationship that you see there.
Yeah, but beta 0 can be some information about.
Well, how about this?
It's no, we have no use it. You say me.
Well, yeah.
Have 0 quantity or something like that.
Beta 0 might not be useful, yes. But take what you could do on your own. Take a look at the high school and college GPA example. Estimate the model without the intercept, and look at the line that you get. Okay, it's not going to go through the middle of the points as you would expect. So thus you can see how that can distort then the relationship you have between X and Y if you don't include beta 0. If you want to do that in the way that you actually would exclude beta 0 from the model, in R, this is how you would do it. Put a -1 there, and let me just verify that I did get that right. So I usually don't do it. Yeah. Notice you don't see the intercept term. Okay. So most of chapter 3, the remaining chapter 3 is going to talk about residuals. And these residuals give us a lot of good information about our model. So remember, a lot of the underlying assumptions that we have in our model correspond to these epsilons. So we could actually rewrite our model that we have up here so that now just epsilon sub I is on the left-hand side, and yi minus beta 0 minus beta 1 times xy is on the right-hand side. Notice how this is similar to e sub I, which is yi minus y hat I, or equivalently yi minus b0 minus b1 times x sub I. So if you have assumptions about your epsilons, how about we let these e's, our residuals, help us explore those assumptions to see if these assumptions are at least reasonably satisfied. And so that's what we're going to do. This idea of using these e's is referred to as a residual analysis. So we're going to do a residual analyses, you could say, throughout. First of all, some interesting properties of these residuals. The mean of them happens to be equal to 0. You can show that on your own. The variance of these e's can be, and I emphasize approximated here, by using just a regular old sample variance formula to some respect. You know, when we usually calculate a sample variance, how about we call it S squared? We take the sum of your x's minus x bar squared divided by n minus 1. Well, that same idea here, suppose we take the e's instead of the x's, subtract off the mean, well, guess what? We know that's 0. Squared divided by now n minus 2 versus n minus 1. Well, what do you end up with? n minus e. So an estimate then of the variance among these e's is n minus e. It's not exactly the variance, though. We'll see what happens later on in this course. But it's an approximation, we can say. Now note that these epsilons are independent. Are the e's, though? Well, no, they're not. Why? Well, notice in every one of these e's, now I'm going to have B0 and B1 always. That's what screws up the independence. So you might be thinking, well, how can I then evaluate that independence assumption of the epsilons if I know the e's are already dependent themselves? Well, what ends up happening is that, as long as you have a large enough sample size, the dependence amongst the e's often is usually very, very small. The case where this doesn't necessarily occur is when you have, let's say, data measured over time. Where let's say your predictor variable x is actually time 1, time 2, time 3, time 4, and so on. And we'll talk about then how to examine that later on in Chapter 3. Okay. Back in Chapter 2, when we first were starting to talk about hypothesis testing for beta 1, I just threw up this little thing that you would learn about in your very first stat course. If I want to find a standardized quantity, very general terms, I take the estimate minus the expected value of the estimate divided by the square root of the variance of the estimate, and we can often treat these as normal 0-1 random 0-1 terms, random variables, let's say. So what that means then is, what would you expect as a general range for terms like this for a standardized quantity? Numerical range.
Between -3 and 3.
About -3 and 3. Remember if z was a standardized quantity, and if I had -2.576, if I can fit it in there, and positive 2.576 here, I get 0.99. So that's why we say -3 to 3, or say -2.5, positive 2.5, generally speaking. Now, what's often referred to then as a studentized quantity, all of you have heard of studentized quantities before. If you remember the first time you're ever introduced to a T-test statistic before, you probably heard the story about student T's distribution, and thus a T quantity is often referred to as a studentized quantity. Well, what you end up doing there is replacing the things that you don't know, for example, with estimates. That's a studentized quantity. So that then if we wanted to, with our residuals, we could find studentized residuals by taking E sub I minus its corresponding estimate, expected value of the estimate, you could say, an estimate of that, divided by the square root of MSE. We could call that, suppose, E sub I star. This is what we're going to refer to actually as a semi-studentized quantity. And again, the reason is because the variance of E sub I is not exactly MS. It's close. You'll see later on. But for now, we're going to call it a semi-studentized quantity. So, if I wanted, so what does this mean then for a general range for what you would expect all the E sub I stars to fall within? Approximately. -3 to +3, approximately. So what would happen then if you had something outside that range? Would you maybe be worried? Maybe something's not going right with your model then. In fact, that's one thing that we will look at later on. Okay. So using our residuals and our semi-studentized residuals, both of them, we're going to look at 6 different ways that you can screw up your model. Or you could say violations of the model that we have stated so far. First of all, we're going to look at is the regression model linear or not? What I mean by that is what I was talking about at the very beginning here is that basically we have this linearity assumption there. Maybe I should have a quadratic effect instead. Well, that's not linear. Well, how can we maybe use our residuals to figure that out, if that should occur? Yes, we can. The error variance is not constant. No, something I should emphasize earlier. Notice epsilon sub I. Each of the epsilons has exactly the same variance. So if instead, let's say maybe I had a subscript I on that sigma squared, that will allow me to have different variances for each of the epsilons. Well, that's a different kind of model. What we're going to talk about right now is models that have a constant variance. So can we maybe use the residuals to figure out if this assumption is violated or not? Yes, we can. Chapter 11 actually talks about what happens if you did have a subscript I there to allow for different variances. So the epsilon i's are not independent. Well, how could you determine that? Well, maybe you could do some kind of plot of the residuals and look for some kind of particular kind of trend, and we will do that to see if there's dependence. The model fits all but one or a few possible outlying observations. Well, we're going to look at how to determine that. The epsilon sub i's are not distributed normally. Again, the epsilon, that was one of the big assumptions. Well, we're going to use our semi-studentized residuals to help us determine that, if this is true or not. And then also, maybe we're not accounting for other important predictive variables, such as like in the high school and college GPA example, maybe we need another predictive variable in our model, let's say involvement in school activities in high school. Maybe we should include that. Well, by looking at the residuals, we're going to be able to make that determination if this is really true or not. And the whole reason why we're interested in examining our model and the corresponding assumptions behind it is because if our assumptions are incorrect, well, might as well just throw out what we're doing. Put it in more statistical terms. For example, when we do a hypothesis test, we state a type 1 error rate, such as maybe 5%. Well, if our assumptions are not satisfied with our model, then all the derivations that go behind driving your test statistic, its corresponding distribution, are not necessarily going to hold true, and so that maybe your type 1 error rate is something different. Maybe instead of 0.05, maybe it's actually 0.5. Well, that's a problem. You don't want to commit type 1 errors. And so that's why it's so important to know if your assumptions are at least reasonably satisfied with your model. Okay. So page 8. We're going to take each of these 6 one by one. Yes?
Are there any considerations regarding the response variable that may affect the one? Like, for example, if I'm measuring a disease in plants, I'm trying to relate a number of scores of numbers with the severity of disease. I measure the severity visually, but my response variable is like category 1, 2, 3, 10, and each category belongs to a set of ranges.
Yep.
Would that have an effect?
Yeah, because, remember with that epsilon assumption, and I think saw this first at the end of chapter 1, with that epsilon assumption for normality, that means Y has a normal distribution. And if you have categories, let's say they're ordinal categories to make this easy, 1, 2, 3 up to 10, that's not a normal distribution. You're a fixed number, 10 different categories, and you're assuming that, with a normal distribution, you have a continuous scale. So obviously that can be a problem. What could occur is that perhaps then, maybe a normal distribution might be a nice approximation to what you're doing. If you did a histogram of how everything fell into the categories and looked kind of normal, well, maybe this model might work out well. Alternatively, what you could do is apply some stuff from Stat 875, categorical data analysis, where now you acknowledge the fact that your response is categorical in nature, and in your particular case, there's what's called a multinomial regression model that could be used for that. So take Stat 875 if you want to know more about that. I'm teaching it next spring. I'm also writing a book on it too. So buy my book, take the course, everything will be good. One of the main purposes of this kind of course is to get you some exposure to the basics of regression modeling. There are tons and tons and tons of other stuff out there. This is, just to get you started. I could say that Y has, let's say, maybe a Poisson distribution. Well, we're not going to talk about that here. We talk about it in 875. I could also say maybe in addition to having this as my model with an epsilon there, maybe I have an additional term, let's call it eta, that also has a normal distribution to it. This is what's called a mixed effects model. Where would you discuss that? Well, you would talk about those starting in Stat 802, but you also hit on this, especially in probably 970 and definitely in Stat 971. Suppose instead that my model looked like this. Beta 0 plus x raised to the beta 1 power. This is called a nonlinear regression model. That's what it's the subject of. I think it's Stat 974. I think that's what the course number is. Perhaps I'll repeat myself. The purpose of this course is to give you basically a good foundation into basics of regression models, because the stuff that we do here then applies to all these other courses I told you about, but just small changes to it. Okay. But I mean, that was a good question that you had. Let's see. So, number 1 here. The regression model is not linear. Again, this assumption here for our model is a linear model. And how can we make a determination of basically our models misrepresented? Well, what you can do is this. Plot your residuals versus x. If the points end up being a random scattering, everything's okay. There's really no evidence against your linear assumption. If, however, though, there's a certain pattern amongst those residuals, that's when you need to start being worried that maybe there's something wrong with this linearity assumption that you had. And we'll discuss why shortly, why patterns are important to look for. In our particular setting, when we only have one predictor variable itself, a plot of E versus y hat will give you similar information. And in fact, you could somewhat look at a plot of y versus x too and get some similar information. But later on, when we have more than one predictor variable in the model, you're not going to be able to get that same kind of information. So we will have to rely on plots such as this. So here's a simple example. Now obviously, power companies, electric companies, they need to be able to judge how much capacity in terms of electricity to generate so that there's no power outages. And how would they make that determination? Well, they're using some kind of statistical models in the background to decide, okay, if I have maybe, let's say, a high temperature, if I expect a high temperature of 100 degrees today, I know that, I should be, generating at least this much electricity. That's a simplistic explanation, but that's generally speaking what they do. And so here's again a simplistic way to look at things. Let's let Y be my peak power load that the power company needs to have available. And let's let X be the corresponding temperature. And suppose a random sample of 25 summer days are selected. And so my data is in a file called power.txt. It's plain old ASCII text file. Read it in like I normally would. I'm going to use the head and tail functions with the object that I create with the read in data. So I can look at the first 6 and the last 6 observations. So the first observation, temperature was 67 degrees. Peak power load that was needed that particular day in the past was 96.5. There was one day where I had a high temperature of 108, and the peak power load needed that particular day was 189.3. So this is historical information in case I didn't say that before. And we like to estimate a regression model to help understand the relationship between temperature and peak power load. So what I'm going to do is, I'm going to do a simple scatter plot of my data, in very much the same way as we've done before. And this is what we got. So as you would expect, as temperature goes up, seems like peak power load goes up as well. We would like now to estimate a regression model to help us get a better understanding of this relationship that we see. Okay. So, using stuff that we've learned before, I'm going to use the LM function. My data is in power.load. The formula that I use for my model itself, I have load as the response, temp as the predictor variable, put the results into mod.fit. I'm going to then summarize the mod.fit as well, and actually save those results so I can do some stuff with it later, and then say sum.fit. And so there's the results from fitting my model. So let me go back to Word here. My sample regression model is, this is how I would write it, something like this, power hat is equal to negative 47.39 plus 1.98 times temperature. Notice this Ttest here. Wow, very small p-value, saying that there's sufficient evidence of a linear relationship. We've got to be careful there, though. We'll see why coming up. How about I do a plot on my residuals versus x? So on my x-axis, I'm going to put temperatures. My y-axis, I'm going to put residuals. Remember how I get the residuals out? I simply pull out the component residuals from mod.fit. I'm going to put an x-axis label, y-axis label, color of the plots, open circle, and put some grid lines. And I'm also going to draw a horizontal line at 0, make it a red color, because remember, on average, residuals are equal to 0. So before. This is what I get. So do we see any trends in this plot? Is this a random scattering of points? No. So we have positive residuals for low temperatures, positive residuals for the high temperatures. I'm sorry, for the higher temperatures. We have negative residuals for the middle temperatures. So notice what this means then is our model here is underestimating y. Because remember, y minus y hat is a residual, so y hat is less than y. The model also is underestimating y down here. And if you're using this model to predict power load, that's a problem. You might not have enough power generated then if you're just using this model alone. So what this is evidence of is that we have a problem with our model. That this linear relationship is not necessarily working out here. And because we only have one predictor variable, we can also see this by doing a scatter plot of the data with the sample model on it. So notice here how the points are above the line. Up here the points are above the line, and generally speaking the points are below the line down here. So that if I could, what you might think then is that maybe the actual relationship is something like this, right? In other words, a quadratic relationship. And thus that's a violation then of saying beta 0 plus beta 1 times x only. Okay. So how would I include now, let's say maybe a square temperature term in the model? Here's how. Use exactly the same model formulation that you did before. I'm sorry. Let me say one thing first. This is the model that I want now. Power hat is equal to B0 plus B1 times temperature plus B2 times temperature squared. That's the model that I want now. Now you might be wondering, well, why didn't I just put a square, let's say right here, and not have that at all? Well, the reason being is because that causes, you could say, odd shapes to the actual curve that you're doing. Similar to what we were talking about before, if you exclude B0 from the model, that will cause maybe some unintended consequences of how the line fits through the points. The same thing will occur here if you don't actually include, let's say, the non-squared term with the squared term. We'll get into more details about why we do this in Chapter 8 when we talk about these models, polynomial models in more detail. But right now what I want is this model. Okay? And this is how I can do it in R. Formula equal load tilde temperature. And then whenever you have another term in your model, you simply say plus. This doesn't mean you're adding stuff. It just says basically and. And to do the squared term, I say temp caret sign 2. Just like how you would do, for example, if I do 4 caret sign 2, I get 16. But there's one other little component that you need. And that is, you need this I function around all that. The I function stands for identity. And basically what this means is that you want R to interpret temp caret sign 2 as temperature squared, as you had intended. If you don't do that, and this kind of gets complicated here until we get into later chapters. If you don't do that, R will interpret this differently. Because that caret sign 2 in a formula argument actually has a different meaning than what we want it to. Sorry to say this again, but wait till Chapter 8. For now, believe me, indeed, you need to have the I function around it. Sorry, we can't talk about everything exactly everything all at once. So to get this, the square term there, you need the I function. Once you do that, put the result I'm going to call mod.fit2. I'm going to summarize the fit, and here's the important stuff, located as you would basically expect. So B0 is 385, B1 is negative 8.29, and B2 is 0.059. How about now with this model, we actually plot these residuals again versus X. This is what we get. So basically I take the same code that I did before, but now I have mod.fit2 $ residuals. Notice it's a random scattering. When you see something like that, you should smile because that means everything's okay. The right-hand side plot, what I've done is actually plotted then this quadratic model that we just estimated. How did I do that? I used a curve function just like what we've done before. Here's B0, here's B1, and now here's B2. Notice I can, in this case, put X caret sign 2 there. Just the formula arguments, you have to worry about that caret sign. And then when I plot the model, there you go. Notice how now that line goes to the middle of those points. So this looks like this is a good model. Any questions? I think this might be a good place to stop. So that's it for today.